for coming to this webinar today. This is the first KITP Innovate seminar for NSBP that we have for the year of 2025. And we are happy to introduce Joseph Moscoso, who is a PhD candidate at UNC Chapel Hill. So I'll give a brief introduction to Joe and then let him start his talk today. So Joseph Moscoso is a PhD candidate at the University of North Carolina, Chapel Hill, and Professor Amy Nicholson's Lattice QCD group. He did his undergraduate studies at Florida International University and is a McNair Scholar. He was awarded the National Science Foundation Graduate Research Fellowship and is currently at Lawrence Berkeley National Laboratory with the Department of Energy Office of Science Graduate Student Research Program. So today, Joe will be talking to us about Lattice QCD, and the title of this talk is Towards Calculations of Neutrinoless Double Beta Decay from Lattice QCD. So take it away, Joe.
Okay, well, thank you for the introduction, Alan. And I appreciate the invitation by KITP and NSBP for this opportunity to give kind of an overview of my research in Lattice QCD, as well as the global effort for neutrinoless double beta decay. So I'm going to just test. My title for my talk is Neutrinoless Double Beta Decay from Lattice QCD. And I'm going to give kind of a broad overview of the status of neutrinoless double beta decay in terms of the experimental discovery of this and the approach that we're taking in the Lattice QCD community toward enabling discovery in these experiments. And as the introduction said, I'm at the University of North Carolina, Chapel Hill for my PhD. I'm a PhD candidate, and I'm currently at Lawrence Berkeley National Lab pursuing finishing up my PhD studies. So I think we'll just start from here. And the story, as usual, begins in the standard model of particle physics, where we have a classification for the fundamental forces that govern our universe in terms of these fermions and bosons. In the standard model, we have quarks and leptons, and these interact with gauge bosons. And so the standard model has been termed the most successful theory in, I guess, human history, because with just these, 12, 16, 17 particles and their antiparticles, we're able to describe, or we should be able to describe, all observable interactions in the universe. And really where I focus as a nuclear physicist, sorry, I saw a hand, never mind. As a nuclear physicist, is in the investigation of the strong force, which is the sector of the standard model that governs the interaction of the quarks, which is up, down, charm, strange, and top of bottom, in case you haven't heard of them, with the rest of the fundamental particles, like the leptons, the neutrinos, and how they interact via gluons and the heavy gauge bosons. So the strong force, I'm trying to move this window here. Sorry, give me a second. I can't see the right side of my slides. Okay. All right. So the strong force here is governed by the force we call Quantum Chromodynamics, or QCD, and it's really just it really explains the broad variety of nuclear hadronic systems that we observe, including the protons and neutrons, which we call this big N here, nucleons, and their interactions with the lighter hadrons like pions. While the electroweak force, which is the other main force involved in neutrinoless double beta decay, governs not only the interaction of photons with these charged particles, but also the weak interaction that results in things like nuclear beta decay and radioactivity. And the real caveat here is that the standard model has this built-in prescription for the neutrinos, where they're chargeless, they interact with the rest of our particles via these W and Z bosons, and that they're massless. And really, the success of the standard model can be seen in, for example, in the 2012 discovery of the Higgs boson, which really completed the standard model and gave us this simple or relatively simple Lagrangian that describes all of space-time interactions and how our universe has gotten to the point where we are. But that wasn't exactly the full story, since in the late 90s, I think, there was this first discovery of beyond the standard model physics or new physics in neutrino oscillations. And really, this discovery proved that neutrinos have to have mass, even though in the standard model it says they don't. And so this became a big problem because the standard model fails in the sector of the electroweak sector, and such a fundamental particle as the neutrino, where else can it fail, or how else can we find these failures, right? And that's really where we are in today in we call like the precision era of the standard model beyond the standard model of physics searches, where a lot of the questions that are still left unanswered, like for example the neutrino mass, the origin of the neutrino mass, what are the different masses of the different neutrino generations, what is their hierarchy, origin of dark matter, and the origin of the matter antimatter asymmetry. Just these small problems that we think about on the daily, but really they should be able to be approached through the standard model and its interactions. And really in nuclear physics, we played this role where in searching for these new standard model interactions, we have this experimental efforts that uses nuclear systems as experimental probes, for example, with electron-neutron scattering, electron nuclear scattering, neutrino nucleon scattering. And on the theoretical effort, we're trying to refine our understanding of the standard model, how we can go from the standard model to these hadronic particles, and how the QCD governs their interactions. So here we have this figure from Vincenzo Sirigliano, who has led the effort to understand this new standard model in terms of these precision measurements and these neutrino nuclear systems. And really, the main experimental efforts we're looking at is neutrinoless double beta decay, and as well as also important the neutrino nucleus interactions like happening at Dune. But for today, we'll focus on neutrinoless double beta decay. And so, to give a introduction to neutrinoless double beta decay, we can always remember beta decay, which is when you have the transmutation, as they say, of a heavy atom like germanium or uranium, and what we see coming out is an electron and well, really an electron, and we see a different atom coming out, or different elements. And on the few body scale, this looks like a neutron transforming into a proton, an electron, and emitting neutrino. And really, the origin of the neutrino came in the discovery of beta decay and the implications that there was some missing mass in the spectrum. And so neutrino and so double beta decay is this process happening in a finite space-time extent where you have this double transmutation of two neutrons to two protons, and as well two electrons, and in the traditional sense, two neutrinos. And double beta decay, which is on the bottom left here, really has this observable spectrum where it's very broad, and you have a range of energies where your electrons can come out. That's at the bottom. And this is a very well understood process. I mean, it's very rare in the standard model, but it's well understood, first observed in the 80s, and now we're really trying to refine our understanding of it. But this neutrino-less process that's in the top left is not allowed in the standard model, for example. And the implication of this neutrinoless double beta decay and why it's important is that if it were to be observed, right, it would be new physics, it'd be beyond the standard model, but it would give us a mechanism for lepton number violation. And in the standard model, there's a conserved quantity, which is the number of baryons minus the number of electrons, if you minus L. And neutrinoless double beta decay would be a clear smoking gun of a process where this is not conserved. So as long as this beyond the standard model physics, that'd be a clear signature experimentally. But theoretically, would have implications for the origin of, for example, the antimatter asymmetry, right? And then on a more QFT or quantum field theory approach, it would also reveal that neutrinos are their own antiparticle, what we call Majorana particles. And that's more for the understanding of neutrinos and the origin of their mass. But as you can tell, this is probably a very important process of this. And its experimental expectations is that will be also a very clear signal in the spectrum, for example, germanium turning to selenium, where you see at the right-hand side of the plot at the bottom that there's a very clear peak of what neutrinoless double beta decay would be at, and it's a very small resolution. So effectively, if you were to see this process, it would be easy to see, if you can get rid of all the background and give you implications for a broad variety of physics. And so, like, as an important experimental effort, we have a lot of collaborations globally that are looking for neutrinoless double beta decay. And I'm focusing on germanium here, but there's a very broad variety of heavy elements that they're looking at this in. But I bring up germanium because that's what the Legend experiment uses. And the Legend experiment has some faculty in my university, so of course they're my favorite experiment. But they're using germanium in these very large ton scale experiments where they fill it full of germanium gas. They try and get rid of all the background, and they wait in order to see if this process will happen. And this is not exactly a new type of experiment. It's been happening since the late 80s, and I mean after the discovery of the neutrino mass. As you can see on the right-hand side here, we have some determinations of the neutrino mass from these kind of experiments. And it's been refined as we come to present day, where Katrin is a experiment that happened before Legend. But as they zoom in, you can see it gets even more and more accurate, but it's not zero. So there's definitely an implication that there's a non-zero neutrino mass, and that these experiments can help refine this prediction. Okay, so to continue from there, I'm not really a neutrino physicist. I'm a nuclear physicist, and when we think about nuclear physics in the sense of from the Standard Model, we want to understand how the interactions of the quarks, leptons, and the bosons give us all the observable mass, matter, and different observations of particles that we see today. And so this is a very broad field, technically, since there are different states of matter, super dense matter, normal low energy matter like protons and neutrons, hadrons, and these things can interact to give nuclear reactions, as well as, for example, neutrinoless double beta decay. So really understanding how QCD in the Standard Model gives you these different properties of our universe is the realm of nuclear physics. And here I give some examples like understanding the nuclear spectrum, which is very rich, understanding nuclear reactions from first principles, which is not as easy as it could be. And these are being looked at different experimental facilities. Here I just give some that I'm familiar with, like at Jefferson Lab and Dune at Fermilab. But to give a sense, nuclear physics also understand not just nuclear systems at an effective level, but how they emerge from QCD. And so this leads us to what is QCD, or quantum chromodynamics. And if you've had any experience with quantum field theories, you know that we can write a Lagrangian for these fundamental fields that from this Lagrangian should give us all the behavior of these fields, right? And so that's the power of these quantum field theories. There's not a large number of Lagrangians it could be because of symmetries, so you can really constrain the kind of Lagrangian it could be. And through historical efforts, we observed this hadronic spectrum, and we came up with QCD. Well, not we, but Gelman and them. But QCD has this different interactions built into it by the Lagrangian, where quarks interact with gluons, but also gluons interact with gluons, which makes it special as no other force, like electrodynamics, the photons cannot interact directly in this way. So there is some special properties of QCD that make it rather frustrating when you try and use it for low energy nuclear systems. So, for example, QCD is not perturbative, so at low energies, the coupling constant of QCD, which tells you if you can use perturbation theory or not, says you can't. And we can observe no free quarks, so everything is built into these hadrons. And so this brings us to the quark model, where we have an understanding that protons, neutrons, and some mesons are very simple systems comprised of 3 quarks. In reality, maybe not. But this is not the full story because, for example, the mass of the quarks that built up a proton do not really add up to the proton mass. So there has to be some type of energy stored in these gluon fields. And there's been an observation of many particles that give us a hint at that the quark model in QCD is not exactly simple. Like their QCD can give us all these different particles, but how exactly it happens is a question. So that brings me to how we treat non-perturbative systems. So we use Lattice Quantum Chromodynamics, or Lattice QCD. You can see it's a mouthful, so I will not say it. But this is a computational method where it's really a mathematical technique that allows us to tackle this non-perturbative problem. And really the highlights that you want to take away from this is that it's not a model. You're directly solving QCD. So it has realistic uncertainty estimates. It's systematically improvable, and you have controlled nuclear effects because you have the privilege of picking different parameters in your QCD Lagrangian, since it's a theory. And it's also made pretty easy because, or not easy, but realistic because computers are relatively inexpensive these days and pretty advanced thanks to GPUs and these supercomputers. So the process for life on the lattice, as I like to call it, is that you have your QCD Lagrangian and you're doing numerical evaluation of these path integrals of your QCD Lagrangian. And this has the power that you discretize your space-time so that you have a finite space-time volume and also a lattice spacing that controls how fine or how high energy you can go, right? Because if you can't go infinitesimally small, you have a limit to what energy ranges you can achieve in this system, right? And the sophisticated approaches to quantizing lattice QCD gives you a preservation of the symmetries of QCD, so that you're really capturing the physics without disregarding too much of the details. But of course, there's problems here. Also, would be just an easy solution. And the problem is that you can't do real-time dynamics because of the sign problem when you have a real path integral. So instead, we do this in Euclidean time, and this gives you a system analog of statistical mechanical time evolution. So as a recap, life on the lattice, you have your finite discretized spacetime that gives certain parameters that you can tweak. Your tunable parameters of QCD are now the ones you pick, like the masses of your quarks, and this has implications that you can be at heavier than physical masses, right? And so instead of being at a physical mass for the proton or the pion, you can create heavier than physical particles, and this has advantages as to make the computation easier. And in Euclidean time, we use Monte Carlo methods, and so it's not exactly clear how you would go from all these different steps into making an elasticity calculation and take it toward understanding physical amplitudes in real time, right? How do you go from these particles in a box to understanding germanium, for example? And this is really the realm of my research, where we call it finite volume physics. And in this we use non-perturbative mappings that once you do your lattice QCD calculation, however you do it, I'm not going to go into that because it's a very sophisticated approach, but once you do this calculation, you get energy levels, right, in your finite box. And how do you take those and give you energies for, let's say, example, the proton? And a simple example I like to use is quantum mechanics, where if you put a single particle in a one-dimensional box, right, you can relate the periodic boundary conditions of your box to the wave function of the particle. And this gives you a quantization condition that we're all familiar with, where the momentum is discretized, right? And so what happens with two particles is that your wave function for these two particles in a box now has this phase shift incorporated into it. And using the periodic boundary conditions, the phase shift will then, the quantization condition will then include the phase shift, which is the connection to the infinite volume physics, as we know from classical scattering. And so this quantization condition, or bar classes of quantization conditions, really give us a direct mapping from on the left, our finite volume space-time energy levels, to our infinite volume observable, which is a delta here. And so this has a simple example, but To derive it in QFT with 3+1 dimensions, this takes a little long, but I'll just give you what the idea of what they're called. Dilution formalism relates your two particles scattering on a lattice to your scattering amplitude in physical spacetime. While the dilution formalisms will then explain how to get matrix elements, for example, K to pi pi, where you have a weak decay. And so this is not it's not a trivial problem because in the space-time lattice, you also break rotational invariance. And so how do you go from a system where you have fixed outgoing angles, for example, to the physical system where at S wave you can scatter in any direction, right? So it's not exactly non-trivial, but these formalisms are advanced enough now where we're able to approach two-body scattering. I'm going to give some example of this, but I just want to touch on that since we have all these parameters in QCD, you have to go through a lot of work to relate them to the physical amplitudes, not only in the dilution formalism, but also by doing calculations at various lattice spacings, lattice volumes, and masses of your quarks, because you need to do extrapolations in these different variables in order to get to a physical value. And on the right here, I have an example of GA, which is the axial coupling of the nucleon, and it really is probably the most refined quantity from Lattice QCD we have today. And as you can see in this continuum extrapolation here, which is done by the CALAC collaboration, it takes a large number of not only lattice spacings, lattice volumes, but models to get a physical amplitude. And it's a pretty elaborate process. So you need a lot of calculations to do this. It's not exactly easy. But regardless of that, we have some confirmation that Lattice QCD works. Where here, for example, the row resonance, which is in pi-pi scattering and P-wave, through the work of the Hasbett collaboration, they showed a proof of principle where if you can constrain your energy levels in your lattice enough, you can then explain, for example, a resonance here, where in delta, once you cross 90 degrees, there's a resonance, and so here we would say it's the row resonance since we're in the channel for that. And another one is the lambda 14 fractional lattice, which has been unexplained since the 50s because they were using the quark model. But if you go away from the quark model toward these exotics, you could think of the lambda 1405 in a couple channeled Meson baryon system. So Kn sigma pi scattering, maybe it's in there. And using the advancements in Lattice QCD, we were able to probe using this couple channel system, simulating these particles interacting in a finite volume, the lambda 1405 coming from the Lucian formalism. And so just as a quick flash, we can take our finite volume energy levels and get physical amplitudes and explain properties of particles this way. And so we're at the roadmap for how we get to Neutrinoless Double Beta Decay, right? So we have our lattice calculation, and we really want to get to, for example, the lifetime of Neutrinoless Double Beta Decay in germanium. And so that's not an easy problem because there's various scales we have there. Really, this overarching scale problem is implicit in the fact that you have these beyond the standard model like processes happening, right? Neutrinoless Double Beta Decay. How does that manifest in a low energy nuclear system? Because as you go from those high energy scales where we don't even know what that happens at, there's a lot of physics contained in all those levels. And so the mapping here is that to get our nuclear matrix elements, we need this process of effective field theory and Lattice QCD. And so the roadmap is not exactly a direct one, but I painted it in this way to give as my preference of Lattice QCD, how we go from there to nuclear matrix elements. But what really is the problem with Neutrinoless Double Beta Decay theoretical predictions, right? That's the question. So from a practical point of view, these experiments have different heavy elements like germanium, calcium, xenon, and what they probe is the lifetime for Neutrinoless Double Beta Decay, right? Or what I call here is the zero nu on the left on the plot. On the theoretical perspective, we can calculate this lifetime using our techniques from nuclear many-body theory, where we calculate the nuclear matrix elements, this green part in the equation above. And as well as having some scale for our Neutrinoless Double Beta Decay masses and some phase space factor, we're able to constrain these half-lives for this. On the lower left, on the plot on the left here, this is from nuclear matrix element calculations, which are many body calculations. It's not just two nucleons. It's germanium, for example, and they use many body methods like density functional theory. And the thing there is that it's not exactly well constrained. It's more of a model calculation, so your uncertainties aren't easily quantified. And in this plot here, you can see that for these different atoms of different elements, sorry, there's a various energy scales, right, happening here. Like for example, in the 48 cosmic on the left, you have one calculation happening near 10 to the 28 years, while one is happening under 10 to the 27. So it's if you look upon here, there's a lot of uncertainty in these matrix elements, and the question is, how can we refine these, and where do they come from? And so this is a good place to really question, like, what exactly are we looking for when we want to see this Neutrinoless Double Beta Decay? Because experimentalists know what they want to look for, right? They see a signal at this energy and they see it. On the theory side, how do you constrain exactly what's happening to give you this mechanism? And so we call this LNVs, or electron number violation mechanisms. And in the literature, there's really two main sides here. There's long distance and short distance interactions, where the short distance will be higher energy and long distance will be lower energy. And so I give some example here for a light Majorana exchanges where you can have a propagating neutrino between these contact vertices here. And on the right, a heavy neutrino exchange would be where the neutrino is so heavy it doesn't really propagate, so you can think of this as happening at a finite space-time point. And so these scales for LNV give you different mechanisms, and they really to separate them as, are you above a TeV or are you near a TeV? But that's a really high energy, but it gives you different theoretical prescriptions for how you connect these. But these are all involving these perturbative interactions on hadronic amplitudes, while these hadronic scales are also given by effective field theory. So we have to kind of understand what effective field theory is. And I wanted to give you a primer that you should all be familiar with. Is if you're a spherical cow on the moon, right, and you jump, you can find your gravitational potential energy using this familiar formula from classical physics. While if you're a spherical cow jumping on the moon, and you're looking at it from a long distance perspective, you can use Newton's gravitational equations, but you don't really need these levels of you don't really need to understand what the sun is doing on this cow to understand how it's jumping on the moon, right? So this really tells us that effective field theory is saying, in our ignorance of scales, those are still important. If you're just on the surface of the moon this is Mars here, the surface of the Mars, you don't really need to understand the scales between you and the sun to calculate your potential energy, right? And a more familiar example historically is the Fermi's model for weak or beta decay. Before they understood what the W boson was, they still wanted to make calculations of beta decay for these elements, right? And so Fermi, he created this coupling, or GF here, Fermi's coupling, where beta decay is just a process happening between a neutron and a proton. And after they discovered quarks, they're able to then include quarks in there. But you don't need to understand that there is a W boson being propagated there, because you can then, in your Fermi model, your contact interaction can be built in to give you that probability of beta decay happening. And so EFTs also give you a prescription to how you go from a high energy theory where the W boson lives to a low energy theory where there is some degree of unknown about what's happening at that vertex, and how to match those two in order to give you a scale for what that vertex should be, depending on your high energies, or the other way around. And so we do this with a method called LECs in order to connect these. So let's go back to this NME, nuclear matrix element. Where these uncertainties coming from is how we relate our low energy nuclear systems in Lattice QCD to these high A elements here. And just as an example, you know that the nuclear system is a problem of scale. Before we discovered quarks, we could easily, or we could effectively explain the interactions between protons and neutrons. But once quarks are discovered, we see that there's a vast energy scales going from the level of quarks to your favorite heavy atom. And how can we really connect those, right? And just to give a name on the left here, this EFT prescription for neutrinoless double beta decay really goes through all these scales from BSM physics down to many body methods, and each one has a certain name: standard model EFT, low energy EFT, chiral perturbation theory, chiral effective theory, to our many body methods. And Lattice QCD really lives in the realm of 1 GeV to 100 MeV. And using this prescription, we're able to then refine this model to what exactly we need to calculate with EFTs and lattice to give us these nuclear matrix elements. And so running down these energy scales, we see that the most important contributions are processes between neutrons and protons and these pions. And we can connect these toward these different type of exchange mechanisms. And so now that we understand that our most important processes from Lattice QCD are these nuclear systems, we can go back to our idea of this roadmap and really understand how from Lattice QCD we can probe these systems. And so in Lattice QCD, we have the burden of calculating nuclear matrix elements of just nucleons, so 2 nucleons and 2 protons here. And depending on your LNV scenario, you have different interactions you can calculate in Lattice QCD. So for example, if you do the long distance scenario versus short distance has a contact interaction, which has different scales as a long distance interaction. The long distance interaction has the advantage of including the axial component to the nucleon, which is very well understood, but both scenarios have some degree of uncertainty into how you can really implement this in a lattice calculation, right? And so depending on this standard model extension, you really want to understand the interactions between 2 and 4 quark operators and leptons, and that manifests in the low energy realm as between neutrons and protons. And so in recent literature, you can see the statement that the most outstanding and computationally feasible results needed from Lattice QCD are related to these NN to PP processes. And so if those are where really that's the simplest you can do with 2-body scattering for baryons, we should be able to approach that with Lattice QCD. But the caveat here is that Lattice QCD will never really be able to calculate your favorite isotopes, and it's very hard to even calculate these 2-nucleon systems. So germanium's out of the question. And this is really a lot of different reasons, but one of them is that you know that the nucleon itself, a proton, is about 1 femtometer size, and practically on a computer, it's pretty hard to make systems that are tens of femtometers on a lattice. I mean, 4 to 6 right now is the cutting edge. So including more than 1 nucleon, 3 and 4 gets pretty hard just on a finite box size. There's also a large range of scales here. A germanium atom has individual atoms, which have their own energy scales, as well as the interactions between them. How do you quantify these with Lattice QCD? The tiny energy splittings. A neutron-proton bound system has a binding energy of 2 MeV, while the proton energy is 938 MeV. So that's really a per milli, very small interaction energy between these nucleons. Can Lattice QCD really resolve this with some finite spacing? And then there's a problem of with contractions, how you actually do these in quantum field theory. For the nucleon, it's not that bad, right? But once you get to the deuteron, which is the bound state of two nucleons, there's a large number of contractions you have to do, and for helium, you can calculate them. It's the order of 500,000. So doing these contractions is not only expensive computationally, but it's also not exactly easy to implement. And then there's the famous nucleon noise to sign problem, which really comes from the fact that in Lattice QCD, you're calculating correlation functions. These correlation functions, you extract the energies from them from the long time behavior of them. So for example, this is an example of a nucleon correlation function. You can see that by our understanding of correlation functions, we need to go to late times in order to extract the energy of the nucleon. But what happens at late times, like after t equal to 20, the signal to noise problem blows up. So it's really hard to resolve what actually is the plateau here. And this has some understanding by the fact that if you want to probe these nuclear systems with many core contractions, the QCD vacuum will rather make pions because they're easy to contract. And so your noise is really dominated by this pion signal. And so in order to resolve this, you either need to be able to go to late times, right? Or you need to lessen the mass of your pion. So Not exactly two are not exactly easy to do there either. And the status of this physics search is we're at the benchmark system, the deuteron, and we want to understand how it's resolved from Lattice QCD. You would think that different approaches to Lattice QCD calculations, how you discretize your action, how you resolve your correlation functions, they shouldn't affect your binding energy because that's an infinite volume observable, right? So the question is, does Lattice QCD predict a bound state in these scattering systems? And this is really a caveat of the question because none of these are done at the physical points. We're all doing these calculations at heavy pion masses or heavy quark masses. And that's really a technical reason is that it makes it easier to invert your quark propagators so you can do your calculation easier. But as you can see in this plot here, what you would want is any of them to hit this red star. That's at the physical point. But all of them are above that and have very different error bars. And this doesn't even include some of the other determinations. So what this means is that different groups don't get the same answer, and we don't really understand why. But the current attitude that we have on how to resolve this is we really want to understand how to effectively make deuteron operators in our lattice QCD calculations so that we can probe the deuteron, right? We want to understand elastic contaminations in our correlation functions and what are the sources of systematic uncertainty at heavy pion masses. And also, what's the role of pion production? Since you have two nucleons, they exchange pions. At heavier than physical pion masses, they probably won't, but as you tune the pion mass to physical, there will be some pion exchange. All of these things resolve in us not really understanding this nuclear system. And an example of this is different determinations by different groups gave us different answers, where some groups in the past have said there's a deep bound state at these systems, while some have said there's no bound state. So how can all these answers be correct? The answer is they can't, and we need to resolve this. And so my work is really understanding this deuteron system from Lattice QCD. And one of the things we're approaching is how do you make these different deuterons in these systems? Like, do you put just 6 quarks on a space-time point and propagate them? Do you separate them into two neutron proton systems? Do you put them in momentum space? Do you boost them? How can you really resolve the system in a finite volume box? And this is an example of what happens at lower than at the physical pion mass is that you get the signal to noise problem, which you can't really resolve since they cut off the time scale here. But if you trust that it plateaus at these time scales, if you do enough of hard work to take away all these different uncertainties, you should be able to then fit it to some plateau region. While on the right-hand side here, we have a very heavy physical pion mass. There, the signal to noise problem is less prevalent, and so we can really hit the plateau. And so my work is really understanding how you go from a space-time volume that breaks rotational invariance and get these systems that are the deuteron lives in a system where you need to be able to disentangle different angular momentum channels, right? Because the deuteron is a mix of S and D channels. So it has contributions from L equal to 0 and L equal to 2. And I'm going from the ground up by using high statistics data. We can project these systems to the irreducible representations of a cube in order to give us the energy levels. And we can resolve the systematics in order to give us a more accurate determination of the deuteron system. And here's a preliminary plot that I prepared that shows that all it really says without knowing how to read the plot is that there's no bound state in the system when you have enough statistics and you do enough work to really nail down these uncertainties. And so my work in this regard is making this a clear pipeline or Python package in order to do all these different techniques in order to get these determinations to use at the physical point. Okay, and then I'm almost done. We have the last part is how you take these determinations of these systems in a finite volume and give us physical amplitudes, right? And so this is from the finite volume to the real world physics. We have different interactions happening. We have fusion, PP fusion. We have interactions between neutrinos and electrons. Can you really put these in a space-time volume that's Euclidean and get a Minkowski amplitude out of it? That's the question, right? And this has been kind of worked on, and this is what I'm currently working on in terms of this N to J plus M system where N and M are stable hadrons. And so how we treat this is that our QCD hadrons are our non-perturbative sector. We use some generic EFT, and we treat all electroweak interactions as perturbative. So it gives us a way to relate these interactions in a box using Lucier and loose-Lucier methods in order to get, for example, the four form factors of these systems. And so one of the main things coming out of these projects is that it gives us a mapping of what exactly we need in a lattice calculation to get physical amplitude. And one of the main things is the finite volume spectrum, two particle spectrum here, so that you can see that in order to do anything for Neutrinoless Double Beta Decay, we really need to understand that two-nucleon sector anyway. But then after that, we have all these other parts of the formalism that must be built in. And just an example for this system where there's only one current coming in. So for example, you go from NN to NP, so one beta decay. You would have to resolve various energy scales as well as understand what the contribution is when this current interacts directly with a stable hadron. And so that leads to a variety of different complications, but especially the triangle diagram where now you have this probing of an on-shell quantity in your perturbative expansion. And so this will be then kind of hard to deal with if you don't understand the implications of this in your scattering amplitude. Because on the right-hand side here, I show that there's actually physical observables that emerge from this triangle diagram. And if you're not careful, you can think that these are effects coming from your transition amplitude that are physical, for example. So you would think, hey, there's some particle being created, so that's why we see some effect happening. Instead, they're not physical, they're just coming from this triangle diagram, and you can really resolve what they are here. And so for neutrinoless double beta decay, we want to understand what happens if there's two currents involved, not just one. So that's really the cutting edge. And there's no easy answer here, it hasn't been fully resolved. But in order to get here, we really need to understand that simpler systems that I just showed. And my role there is to understand it from a nuclear EFT to connect it directly to these nuclear systems, as well as including spin, because these are spin half systems, neutrons and protons, while all the formalisms have been derived only for spinless particles. So it's not trivial to derive these for spinful particles, but it's going to be required in order to approach neutrinoless double beta decay. But really the cutting edge today is how do we do two currents with spin in these systems? And there's not an answer, so I can't answer that today. But there's been some previous work by Davoudi and Kadam that showed that using one of these EFTs where you only have nuclear systems, no pions, nothing else interacting, which is what I'm using for my research, you're able to fully derive this amplitude for neutrinoless double beta decay or neutrino full, either one. But this is being built off of building blocks that you understand. For example, the nucleon axial coupling and this nucleon two-nucleon coupling here, which is not understood, as well as different counter terms. But the good thing about this is that we understand GA really well, to very well precision, while we don't understand G nu and N here. But we can connect that to Lattice QCD calculations. And so the key is that we connect low energy constants in these different EFT formalisms to Lattice QCD calculations of these nuclear systems. And so cutting edge today is how do we determine these LECs, for example, this one in Palace EFT, there's different ones for different EFTs. And with those, you can really calculate the leading order neutrinoless double beta decay amplitude. And this has all been kind of written out in this roadmap for matching theory to experiment for these theories. But what you really understand is connecting these to the nuclear matrix elements is a very non-trivial problem, but it takes many various math scales. So I'm going to leave you with the idea that depending on what your LNV mechanism is, you have different operators that can couple to your nuclear system. And if it's depending on this long or short distance, you have different things you have to calculate. So for an example, on the right-hand side here is if you just think of these short distance contributions, you can resolve them in terms of nuclear systems as specific angular momentums, which you can calculate in the box, and calculate these constants that will then connect to your NMEs. And so the roadmap is really clear, but it's not exactly easy. But Lattice QCD's role is to give input to these EFTs that will then be mapped to NMEs, right? And so I want to leave you with the fact that in the 2023 long-range plan, this has been very much a priority for the nuclear physics community. In order to resolve these experimental discovery, we need theoretical advances, and that only happens by collaborating with not only your local physicists, but globally. And we're not the only ones doing the hard work. Really, the experimentalists are taking the extra steps to go deep underground, build these giant experiments, to get rid of backgrounds. And so, in order to really maximize their discovery potential, the theorists have to do the work in order to resolve the uncertainties in these matrix elements. And so, I'll leave it at that. I'll take any questions after this, but I just want to thank my team. It takes a village to really do all these works, but I've benefited from great mentorship. Sorry. And I want to thank the NSBP for inviting me to give this talk. Thank you.
All right, thanks so much, Joe. We have a couple questions.
Okay.
So from Inkiru, can you briefly expand on what it is about neutrino oscillations that implies that neutrinos have mass? My basic understanding of neutrino oscillations is that it means that neutrinos are changing from one type to another.
So I'm not too much of an expert, but neutrino oscillations, the theory is built off the fact that the mass eigenstates are not equal to the flavor eigenstates of your neutrinos. And so if you could mix the mass eigenstates, or if you could mix flavor eigenstates and mass eigenstates, it necessarily means that there has to be mass eigenstates available. And so without mass eigenstates in your system or in the neutrino oscillations, there would be no oscillations between different neutrinos. So practically, I think that just means that if there's no mass of neutrinos, one neutrino would always stay the same as it goes from one point to another. And it's really built into the standard model because of the fact that the neutrino flavors are mixing. And that's a source today of beyond the standard model physics as well, is constraining how much they mix with each other. And that's done with the PMNS matrix. And it's also synonymous to how quarks couple to each other, right? But the simple answer, I guess, is if there is no mass, there will be no mass eigenstates, and there will be no oscillations or mixing in flavors. So
Right.
hopefully that answers that.
Okay, great. So thank you for that answer, by the way. So Vincent Rogers, I'm gonna put there's two questions here. So, and then we have another from Incura after that. So the Vincent Rogers asked, so the neutrinoless double beta decay suggests that there is both Weil neutrinos as well as Majorana neutrinos. Also, would the Majorana neutrino also get its mass from the Higgs vacuum? And then Vincent Rogers asks again, are the lattice calculations full-blown four-dimensional Euclidean, or is there symmetry imposed to reduce the dimensionality? So I
Okay.
can repeat those if you need.
So the first, let me see this thing. So the first one is asking about if observing neutrinos of orbital decay would confirm its Majorana and Weil.
Yeah.
So I'll interpret. So I'm not too sure about Weil. What that means? Does that mean Dirac fermions as well? I guess you can answer that, but in answering this question, I'm gonna assume that by Weil you mean Dirac fermions, and if not, you can clarify.
Vincent, you can put in the chat as well. But
Yeah,
yeah.
but if observing this process, we would confirm that they're not indeed Dirac fermions. It would have to be Majorana. It's not both, it would be either. Because Dirac fermions, right, they can only be left-handed, so you can only couple left-handed neutrinos, so right-handed antineutrinos, while the Majoranas directly couple the different-handedness of neutrinos. And on the question of the Higgs mechanism, I believe that the Majorana's formulation of the neutrino mass required that the neutrinos coupled to the Higgs field in order to give it some mass. And I think that's really the premise of the seesaw mechanism, where the right-handed neutrinos are so high energy scaled, but they have some mass given to them by the Higgs, but that since that mass would have to be so heavy, it would give some limit or give some boundary on the Higgs. The Higgs would have to be some very finely tuned interaction with that. So if that's the question, then
Well, so he
sorry.
clarifies to say that while is just when the particle and antiparticle are different.
Oh, okay, yeah. So I guess that's what I call Dirac as well. I think they're in the literature kind of synonymous. So yeah, they would, if involving this, because of all the theoretical work that's been done, if they observe this, it's a clear smoking gun as Majorana. It can't be both. while the Higgs question, I'm not too sure, but I'm pretty sure Majorana formulated it so that it has to couple to the Higgs in order to give some mass. For example, to the right-handed neutrinos, and the seesaw mechanism will also involve that. So,
And then are the lattice calculations full-blown four-dimensional Euclidean, or is there symmetry imposed to reduce dimensionality?
so that's actually an interesting question because it's full-blown Euclidean four dimension, right? So you're not in Minkowski, you're in Euclidean time, but the space dimensions are the same. Sorry, what was the second part?
Or is there symmetry imposed to reduce the
Yeah.
dimensionality?
And the symmetry, so really going to the last calculation, when you discretize that action, there's different ways to discretize the action, right? And so it makes it easier with different ways to invert the quark propagators, but effectively what you're doing in the last calculation is you're doing Monte Carlo to estimate the gluon contributions to these propagators. Now, the only way symmetry plays here is once you're in the box and you want to extract the energy levels. You use the symmetries of the box, which you project the box to its irreducible representations, which we call the cubic volume, right? So if you're at rest, you have only certain rotation states. So symmetry there allows you to reduce the amount of work you're doing to get your energy levels. But at the level of the last calculation, I do believe you're fully inverting a quark propagator that has dimensions of the number of quarks you're using, as well as the number of flavors, the number of colors, while you're estimating the gluon contribution. And I'm not too sure if symmetry plays a role there, but I do know that chiral symmetry is not satisfied fully by the formulation that a lot of people use for the action. You need to use a special kind of action in order to then preserve chiral symmetry, but you cannot both preserve chiral symmetry and just do a naive like discretization of your action. So there is breaking of symmetries there, but the symmetries come in when you're really extracting physics from there.
Okay, great. And then Nkiru asks, are you building the Python libraries from first principles, and or is some libraries you are building, are there libraries that you're building off of?
So I imagine first principle means directly. Yeah, everything is done in Python. We do use C bindings in order to make some things more efficient, but the ones I'm making are from first principles in order to correlator analysis, extracting the finite volume energies, and then passing it to Lucier. And the Lucier, all of that is built from first principles. But if we've in the past, a lot of the Lattice community has made these packages that are built off of C, and they're pretty easy to implement in your Python code as well. So numerically, it's probably better to involve both your own codes as well as some of the more historical correlator analysis codes, just because it is a very sophisticated problem. These correlators are massive, file wise, but in terms of if you want really high statistical data, you're working with a lot of data, and so Python effectively gets a little slow. So there is some C bindings that you can use. Mine is built directly off of Python.
All right, thanks for that. I actually had a question. I was thinking of asking you because I know that so Lattice QCD helps with neutrino full
Mm.
uh double beta decay and with the Gamow-Teller transition. Um, but I guess like one question I had like in there towards the end of your slides where you're talking about going from Euclidean to Minkowski, um, how is your wick rotation impacted by this? Are you using a wick rotation or kind of like building that from scratch?
Mm.
Or
So, okay, so I'm gonna address first. You said something about uh, neutrino full. I don't know if you were asking about that, but I just want to mention that you really need to also understand neutrino full beta decay, not only experimentally but theoretically. But theoretically, it's a little more understood just because there's been a lot of work in it, including like, for example, QED lattice calculations, which is a propagator of photons, and that has also led to understanding propagator of neutrinos. And so if you have neutrinos coming out, that's neutrino full. When going from the finite volume to real world, for example, like this here, right? You're asking what happens to the Euclidean part? Now, the caveat there is that since we're using these formalisms, right? These formalisms are built off of generic EFTs in Minkowski spacetime. Now, for example, the Lucier formalism, you don't really need to understand anything about your time because we do all our calculations at a for example, temperature equal to 0 where there is no time extent. And so That's what I mean is that even with the looser, it's kind of hard to understand how to get Minkowski amplitudes. But here, what you do is you do a mapping between your Euclidean amplitudes and your Minkowski amplitudes, and that includes, for example, integrals over time. So it is not exactly a simple, trivial answer to say what we do with the Euclidean time, but it's really built into how you construct these generic EFTs, how these formalisms map the energy levels to your finite amplitudes. And those, at least for our systems, I think we do at 0 temperatures, which mean that time is not really part of our problem. If you do finite temperatures, that means that or you do finite temperatures, that means that your time extent for your lattice is comparable to your space extent. And so you have to understand these temporal effects. But for us, all we need to understand in time is the Euclidean time behavior of the correlation functions. That gives us an energy, and from there we're able to map it to a physical amplitude. And so the Euclidean time dependence gets washed out in that formalism.
Okay, thanks so much.
That answers the question.
Okay, so we have somebody said thanks for the nice talk. Yeah, so thank you everyone for coming, and thank you Joe for giving this wonderful primer on Lattice QCD and helping us get into some of the more granular details. Um, and yes, so KITP is the institution that was hosting this, and we look forward to seeing more of you at these NSBP Innovate seminars. We have some coming up, and thank you for watching, and we hope that you will be able to look back at this on KITP's website as well. So thank you so much.
All right. Thank you, everybody.